Welcome to Brain Vision.
We are given the molar heat capacity of a certain substance in the following form. So we can see that this molar heat capacity is in the form of some constant A plus some constant B multiplied by the temperature T. We also know that the heat required to change the temperature to a different value, we can use the equation dQ is equal to Nc dt, where N is the number of moles of the substance that needs to be heated. So to get Q from here, we can see that if we integrate both sides, we get that Q is equal to N, which is a constant, times the integral from one temperature to the next, T1 to T2, if these temperatures are in Kelvin, multiplied the integral of C, which is a function of the temperature T with respect to T. So if we denote C by A plus BT, we can then conduct this integral. So this integral is N into, and then we calculate this integral, we get A into T2 minus T1. Remember that here C is equal to A plus BT, so it makes the integration fairly trivial. Plus, and if we integrate BT with respect to T, we get B over 2 times T squared. And if we evaluate that from T1 to T2, that's B over 2 into T2 squared minus T1 squared. So here we have an equation which we can use to find the amount of heat required in terms of the number of moles and a change in temperature. So we can apply this equation for our substance in raising N, which is 3 moles of the substance, from a temperature of 300 Kelvin to a temperature of 500 Kelvin. So that's 27 degrees to 227 degrees. So A, we do our multiplication, is 29.5, and that's joules per mole Kelvin, and multiplied by the temperature change of 500 Kelvin minus 300 Kelvin plus B over 2, so that's 8.2 over 2, which is 4.1 times 10 to the minus 3 joules per mole Kelvin squared times 500 Kelvin squared minus T1, which is 300 Kelvin squared. So if we conduct this integral, we find that the amount of heat required to raise 3 moles of the substance from 300 Kelvin to 500 Kelvin is equal to 1.97 times 10 to the 4 joules.